Hello, everyone. My name is Andres Cristi. I'm a postdoc at the Center for Mathematical Modeling at the Universidad de Chile. And soon I will move to EPFL to start as an assistant professor. And today I'm presenting this joint work with Bruno Siliotto called Profit Inequalities Require Only a Constant Number of Samples. Now, what's a profit inequality? It's the following model. Let's say we have an item, a resource we have to allocate, a single item we have to allocate among some agents. Let's say we have n agents. Each of them has some valuation for the item, but these agents are not present at the same time. They come in a sequence one by one. So when an agent comes, they reveal the valuation, and we have to decide immediately whether we give the item to this person. So we want to decide a rule. We want to design a rule to decide when to stop this sequence. And all we're given is the distributions these values come from. So on the first day, we observe a value x1 drawn from a distribution f1. And maybe we decide we don't want to give the item to this person. Then the next person comes, we observe the value drawn from the next distribution f2, and so on until we decide it's a good time to stop. Now, the distributions are given to us beforehand. The values are independently drawn from these distributions. And as I said, our objective is to maximize a stopping policy that maximizes the expected value that we select. A classic result by Krenger and Sachestan says that there is a stopping rule that guarantees that in expectation, we get at least 1/2 of the expectation of the maximum. And this is called the profit inequality because if a profit that sees the future does this stopping game, then since the profit can see the future, the profit will get the maximum value. So that's why this is called the profit inequality. We can guarantee at least 1/2 of what the profit would get. Now, there are several variants of this problem. And let's denote by C star the competitive ratio. That means for a problem, we say the competitive ratio is C star if there is an algorithm, a stopping rule that guarantees a C star fraction of the expected maximum. The classic variant is the one I presented to you, is the fixed order variant. We can get a 1/2, and that's best possible. If the distributions are all the same, in the IAD variant, we can get a 0.745 fraction of the expected maximum. And this is, again, best possible. And there are other two important variants. The random order variant, where we're given distributions f1 to fn, but the realizations do not come in this order, but instead in a uniformly random order. And the fourth variant is the free order one, in which we're allowed to decide in which order we will observe each of the random variables. And in these last two, we don't know what is the optimal competitive ratio. Our question in this work, however, is not what is the tight competitive ratio, but instead, what can we do if we don't have distributions, but instead we only have samples? If we are thinking of doing this in a real application, of course, we don't have distributions, but instead we have data. And normally the distributions are coming from the data. However, in real life, we don't have normally an unlimited number of data points. We have only a bounded number. Let's say we're doing this allocation now in May, and we have data from the last 3 months. So for each distribution, we only have 3 data points. Certainly, that's not enough to learn what the distributions are. So, and this is the question we consider. And the model is, we have these distributions f1 to fn, but we don't know them. we only have a bunch of samples from each of the distributions. So from F1, we have 3 samples. From F2, we have 3 samples, and so on. And we have to design a stopping policy based only on these samples and not on the distributions. And our main question here is how many samples are enough? How many samples do we need to guarantee what we could guarantee if we had distributions? So C star is that value. How many samples do we need to guarantee C star minus epsilon? We have all these 4 variants, and for two variants, for the classic one and the basic IAD version, we know how many samples we need. For the fixed order case, there is this amazing result that says that a single sample per distribution is enough to guarantee a competitive ratio of 1/2. And of course, this is tight because even if we know the distributions, we cannot do better than 1/2. And for the IAD case, to get the 0.745, we know that we require only 1/epsilon samples per distribution. And this is tight, so we cannot go all the way to 1 sample per distribution. With 1 sample, we can guarantee 1/2, but we cannot go all the way to the 0.745 that's possible in the IAD when we don't distributions. In this work, we answer this question for these 2 other variants, the random order and the free order case. And for both, we prove that a constant number of samples per distribution is enough to guarantee the optimal competitive ratio, even though we don't know what this optimal competitive ratio is. Now, a naive approach would be to use the empirical distribution obtained from the samples. However, if we only use algorithms as a black box, the best result we can hope for is the following. If we have empirical distributions or some estimate of the distributions that have good multiplicative error in terms of the upper part of the cumulative distribution function, then we can get the same guarantee as the algorithm gets with the real distributions. However, if you look closely to this requirement, we need that the estimate gets better and better as f gets closer to 1. And this is not possible actually using empirical distributions if you don't have an upper bound on the support. The empirical distributions have a small additive error. And small additive error is not enough to have a guarantee like what we need for this other result. When f gets closer to 1, we need that the guarantee gets better and better. However, additive error stays constant in the whole range. And the reason why empirical distributions only give us an additive guarantee is roughly the same reason why for applying a black box algorithm, we need this guarantee that improves as f gets closer to 1. We can have distributions that have heavy tails. Look at this example. A distribution that is 0 most of the time, and for a large number k, has value k with probability 1/k. If we have less than k samples with high probability, we will only observe zeros in the samples. So there's no way we can capture with samples this part of the distribution. Moreover, notice that the expectation of this value is 1. So it could be that with a constant number of samples, we only observe zeros. However, this variable is super heavy for the objective function. So how do we get around this problem? We proved that we actually don't need to know the upper tails. And more precisely, we prove the following. If we have an instance distributions f1 to fn for any of these variants of the profit inequality, and we have a number m and a small number alpha such that the probability that the maximum is larger than m is smaller than this number alpha, that is small value alpha, then there is an algorithm that takes m and alpha as input and only needs to know the distributions in the range 0m and guarantees a competitive ratio of C star minus alpha. So this result says that if we have this bound M, we don't need to know the distributions after M to get C star minus alpha. And this is very good because if we can estimate things well below this M with an additive error, we don't care about what happens afterwards. So we don't need actually to get any estimate beyond this M. So it will be very helpful for getting our result. And the proof is based on the following claim. If in any instance of a given variant of the problem, we can guarantee C star, a competitive ratio of C star, then there is an algorithm R prime that not only guarantees a competitive ratio of C star, it also guarantees that it gets to observe the realization xi before stopping with probability at least C star. So with probability at least C star, it has the option to select xi. And of course, if we have heavy tails, like large values that occur with very small probability, having the option to observe is what saves us from the fact that we cannot estimate these tails. Now, why is this claim true? Well, we can write the following min-max problem. Let's say we're playing a game. We're given and we're fixing an instance of the problem. So we fix the distributions. We're playing a game against an adversary that chooses some weights beta. And we are choosing an algorithm for the problem. And our objective now, instead of maximizing this competitive ratio, is maximizing beta 0 times the competitive ratio times plus beta I times the probability of observing xi before stopping, right? So now the adversary decides what's important, the competitive ratio or observing the values. And we design an algorithm. We can show that this game has a value at least C star. Why is this? Because we can transform the instance into another instance where this objective is just the regular competitive ratio. If we take an instance x1 to xn, we can create values yi that are beta 0 with probability 1 minus delta, beta 0 times xi, the original value, or with tiny probability delta, the variable is beta I over delta. So this part is expectation beta I. And on this instance, we can prove that the expectation we get is actually the objective value in the objective function of this min-max game. And therefore, since we can guarantee C star in any instance, in particular in this instance, in this other game, in this min-max game, we can guarantee C star. And because the objective function is in the min-max game is linear on beta and linear on the algorithm, if we consider randomized algorithms, then we can exchange the min with the max. And that means that we have an algorithm that is good for any vector of weights beta. So it doesn't matter if we care about the competitive ratio or we care about the probability. With a single algorithm, we can get C star in all of them. So that's the first part of our argument. Because of this, we don't need to know the upper tails because there is an algorithm that gets the chance to select things with probability at least C star, and not only has the competitive ratio of C star. The second part of the proof relies on this definition. We say that a variable is epsilon small if the probability that the variable is exactly 0 is at least 1 minus epsilon. So most of the time, the variable is 0. And otherwise, if it doesn't satisfy this constraint, we say the value is epsilon large. Now, how do we use this? First, we have the second step of our argument. We can reduce to the case or to instances where almost all variables are epsilon small. And in fact, only a constant number of variables are epsilon large. So n, the number of the length of the sequence could be very large. However, we only need to consider instances where the number of random variables that are epsilon large is a constant. I won't give you the whole argument, but essentially, there exists a threshold, some number b, such that if we ignore every value below b, ignoring means assume they are 0, then the expected maximum value is almost the same. It doesn't change much. And most variables, all but a constant, are epsilon small. So this is step 2. All but a constant are epsilon small. And step 3 of our argument is that if we have a bunch of epsilon small random variables and they come in random order, the sequence looks as a sequence of IID random variables. We can pretend that the epsilon small variables are IID. I won't give you the formal argument, but the intuition is that in this sequence, most of the time, we only see zeros. And every particular distribution, every particular random variable is 0 most of the time. So it almost looks as an IID sequence. Now, having these steps, remember the first one says that we actually don't need to know the upper tails. There is an algorithm that gets around that. And the other two steps, steps 2 and 3, essentially say that all but the constant number of variables are IID. We can prove our result. Using a constant number of samples, we can estimate very well the few epsilon large distributions. There are a constant number of them. So with the constant number of samples, we can estimate all of them very well, except for the tails, because the tails can never be approximated well. Then we estimate very well this IID distribution, this distribution for the IID random variables, the epsilon small random variables. Since we have constantly many but times n, we have lots and lots of random of samples of this IID distribution. So we can estimate it very well, except for the tail again. And then we just run the optimal algorithm that doesn't use the tails, that is guaranteed to exist by step 1. And that's how we can get the optimal competitive ratio using only a constant number of samples. Lastly, our result not only implies that we can get the optimal competitive ratio with a constant number of samples per distribution, it also implies that we can get such an algorithm in polynomial time. With constant number of samples and in polynomial time, we can construct the algorithm. And it's essentially a consequence of the fact that we can encode all feasible algorithms with polynomially many linear constraints. So we can write the following linear program we want to maximize the competitive ratio, let's call it beta, such that the algorithm is feasible. These are polynomially many constraints, and the conditions that are guaranteed by step 1, that the competitive ratio is at least beta, and the algorithm observes each variable with probability at least beta. This linear program has value at least C star, at least guaranteed by step 1. And it has polynomial size because first, we can plug here not the true distributions, but the empirical distributions. And notice that since we are using constantly many samples, the support of the empirical distributions is just the set of samples. So the support has polynomial size. So all these expectations and probabilities, they live in a world of polynomial size. And second, something that is not explicit here, but in our problems, in both the random order and the free order, we have to consider all possible permutations of the sequence. However, since we can assume that most variables, all but a constant, are IAD, the relevant permutations are only very few. There is a constant number of relevant permutations. And with these two ingredients, we obtain a linear program that has polynomial size, which means that we can find the optimal policy in polynomial time. So to summarize, we conclude that for all 4 variants of the single choice profit inequality, fixed order, the IAD, the random order, and the free order variant, a constant number of samples per distribution is enough to get the optimal guarantee. It's based on these 3 steps. Step 3 is specific to random order. So we cannot generalize it beyond the random order variants. But it's key to go from polynomially many samples to a constant number of samples. And interestingly, step 1 is a very general argument that allows us to ignore the tails and is not specific to these problems, to these variants. It can be used in other variants of the profit inequality, importantly, combinatorial variants, where let's say we can select many agents, or we want to select the matching, we want to select a combinatorial, we want to run a combinatorial auction. There are many variants where this argument works. And this argument is enough to get a result saying a polynomial number of samples is enough to get the optimal competitive ratio. So we think this could be very helpful for many other problems to prove optimal guarantees using polynomially many samples.